Okay, all good with the QR code? So my voice might be a bit different today because I'm not feeling 100%, but it's still me, okay? You know that it's me on the audio. So let's look at the 3 statements together. So the first one is related to what we discussed on Monday. So in a selection on observables design, ATE, ATT, and ATC must be equal if the CIA is met. So the CIA is the conditional independence assumption. So is this a correct statement or not? Okay, this is indeed a false one. When we have selection on observables, basically there is selection bias in general. We can only eliminate selection bias within subgroups defined by the observed characteristic. So we only have the ATE, ATT, and ATC equivalent within subgroups defined by X. But when it comes back to the general level, they are different. Otherwise, why would we have selection on observables? So this is a false statement. Now, the next one, sort of related to fall back where we have started on the potential outcomes. So here it states that homogeneous treatment effect ensures no selection bias. Okay, is this true or false? This is actually a false statement. Now, homogeneous treatment effect basically means that the treatment effect is the same across all individuals. So suppose we have 2 individuals, individual A and individual B. Then homogeneous effect basically means that the tau, okay, the treatment effect for individual A is the same as that for individual B. So we have homogeneous effect. But having the same treatment effect doesn't necessarily mean that their treated state outcome and untreated state outcomes will be the same. It could be that for individual A, so this individual's treated state outcome, let's say it's 40, and the untreated state outcome, let's say it's 30, then that brings the treatment effect to 10. Now, for the individual B, we could have that the treated state outcome, let's say it's 100, but then the untreated state outcome, it's 90. So in total, that brings the treatment effect also to 10. And imagine that individual A is the one actually in the treatment group, and individual B is actually the one in the control group. Then selection bias, okay, so A is in treatment group. So A is the one that's actually treated and B is control. Then the selection bias is about their untreated state outcome. We want the untreated state outcome to be the same for the treatment group and the control group, but obviously they're different here, although the treatment effect is the same for them. So even if we have homogeneous treatment effect, that does not ensure no selection bias. Homogeneous treatment effect only ensures ATT is the same as ATC, which makes them equivalent to ATE. So this is a false statement. Now, the next one. So a before-after analysis would identify the treatment effect if there is no trend over time in the absence of the treatment, which is sort of related to where we have stopped on Monday. Can this be a true statement, or there's actually something wrong with it? Okay, this is indeed a true one, because the whole idea of that a before-after analysis might not work is that apart from the treatment, there could be something else that changed over time regardless. Therefore, a simple before-after analysis will not recover the treatment effect. And if we do want it to help us to identify the treatment effect, basically we require there's no trend over time. So on Monday, we talk about the minimum wage, the effect of minimum wage on employment. And we have looked at the New Jersey and also the Penn State, which is in the control group. So if you look at the graph that we have here, so you can imagine that the red line depicts the New Jersey, the treated group. So this is the before outcome, so the mean employment level before the policy for New Jersey. So New Jersey before. And the right endpoint is the after. So it's the average employment level after the increase in the wage. Now, if we simply compute the difference between these two endpoints, that basically gives us the before-after change for the treated group over time. And if this were to give us the treatment effect, what we really require is that in the absence of the treatment, so this is the New Jersey's after employment level without the change in wage, in the minimum wage. So essentially, for this before-after analysis to work, we require a parallel line to the x-axis for us to identify the treatment effect by comparing simply the before and after employment level for the treatment group. But we know that in reality, that's implausible. How can we assume that, over the scope of half a year, the only thing that has changed is just the minimum wage? There are a lot of things that has changed. The market condition, the general economic condition, these can all change over time. So such an assumption is unrealistic. And it's really likely that we don't have this, even absence of the minimum wage change, but we do have a trend over time that might look like this. So will instead be here. Then simply comparing the before-after will bias our estimate of the treatment effect. So then we sort of introduce a control group, which is the Penn State. And the Penn State is not subject to the change of the minimum wage. And we sort of claim that based on where we stop, okay? We say that we might be able to recover the effect of the change in wage by simply doing two before-after analysis, one for the treated group and one for the control group. And we hope that the control group will give us an estimate of the trend over time. Then doing the cross-section comparison for the before-after analysis will help us recover the true effect. So essentially, what we're saying is, so this trend, or this difference without the minimum wage increase is not observable. We don't know what actually that trend is. At best, we hope that the change over time for the control group will give us an unbiased estimate for the unobserved change over time for the treatment group, absence of the treatment. Then essentially, there is an assumption imposed here. We really require this difference to be the same as this difference. So a key assumption in the DID framework is that we need to have a parallel trend. And we will discuss this in further details today. So this is just sort of the general picture of how the DID works. Then to set up the framework formally, so let's look at some notations. And just as before, we have two groups. So one is the treatment group and one is the control group. But now there's a time dimension. So we have a before and after. So basically the before is the baseline, it's pre-treatment. And after is the post-treatment period, it's the end line. and the treatment must take place in between the end line and baseline. Then, accordingly, we'll have more potential outcomes compared to before, where we don't really have an additional time dimension. So now we have the baseline potential outcomes as well as the end line potential outcomes. And remember, the superscripts, they represent the potential state, okay? They're not the actual treatment status. So we can see here that we only have one potential outcome for the baseline, which is the untreated state outcome. And this is really because the treatment only occurs post-baseline. So at the baseline, regardless of one is in the treated group or in the control group, they all have the same potential outcome, the untreated state. Okay, so there's no treated state outcome at the baseline. This is just implausible. Therefore, there's only one potential outcome for the baseline, but there are two potential outcomes at the end line, depending on one is treated or one is potentially not treated. So in total, we have three potential outcomes. Okay, so only untreated state potential outcome is plausible for the baseline, whereas both potential outcomes are plausible for the end line. Then, given this definition, the observed outcome would then depend on the set of potential outcomes we have plus the actual treatment status. So at the baseline, given one potential outcome is plausible, the observed outcome is just sort of mapped back to the untreated state outcome. So you see that we have the same notation for those regardless of their actual treatment status is 1 or 0. So everyone is untreated. Now at the end line, those in the control group, they're actually not treated. So we can only observe the untreated state outcome for those in the treatment group, for those in the control group. So the Y naught is the actual observed outcome for those at the end line, whereas for those in the treatment group, their actual treatment status is being treated. So we can only observe their outcome had they actually been treated, which is the Y1. Okay? So we can see that here, it's only this sort of bottom right corner cell is the Y1, all other cells correspond to Y naught. So this is sort of the general setup of the DID. Now, the DID actually helps us to identify the ATT, which is the average treatment effect on the treated Y. So recall how the treatment effect was defined. Essentially, we want to compare the same individual at the same time. It's just that so one potential self is untreated and one potential self is treated at the end line. Therefore, we compare the after. So T corresponds to after, but Y1 minus Y naught. Now, to identify the ATT, basically we take the average of this difference and condition on those in the treatment group, so DI being 1. Now again, the same problem as before applies. There is a missing outcome. Causal inference, it's all about solving the missing data problem. So at the end line, given that you're in the treatment group, everyone is treated. So we never observe the potential outcome at the end line had one not been treated if he is in a treatment group. So the Y naught, so the Y naught after, given DI is 1, is never observed. Then given that we never observed this outcome, there's no way we can compute ATT, and again, it comes back to the problem. How can we find a reliable approximation for this missing data? So the before and after analysis, as well as the cross-sectional comparison, basically propose two possible candidates. One is the untreated self, so those in the treatment group and their actual outcome at the baseline. Or we could actually use the control group end-line outcomes, because the Y naught at the end line for those in the control group, these are observed. But would these two observed outcomes provide reliable approximation to what we have? Now, basically, in the minimum wage example, we sort of discussed that using the untreated self is not a good approximation, because that requires no trend over time. So that requires that absence of the treatment, we need to have a horizontal line, which is unrealistic. Now, one could also attempt to use the end-line outcome for the control group. So if we look at this plot here, so we have this blue line basically correspond to the Penn state. So this is the Penn state before, which is the left endpoint, and the right endpoint is the Penn state after. And Penn state did not subject to the wage change. But if we simply compare the difference between these 2 points, which is our usual observed difference between groups, but it's just correspond to the end line, we know that there might be systematic difference between the two groups apart from the minimum wage difference. It could be that one state inherently has a higher demand for fast food, or one state inherently has a larger, market, more population. So these differences, together with the actual effect of the minimum wage, would give us this total difference, which means simply observing this difference between groups will not help us to isolate the treatment effect from the effect of the systematic differences. So either using this alone or using this endpoint for the control group alone is not a good solution. And therefore, we hope that we can, by using a common trend assumption, so relaxing some of the more restrictive assumptions, to recover the ATT. So this is what we've discussed just now. We hope that absence of the treatment, so this is the trend, this is the trend over time for the control group, and we hope that absence of the treatment will see a parallel trend for the treated group. Then in this case, if you look at the expression, okay, so basically that means the before-after analysis for the treatment and the before-after analysis for the control group in the untreated state, they are the same. Then, in this situation, given that everything on the right-hand side of the equation is observed, okay, and we also have the untreated state correspond to the baseline observed for the treatment group, then the only thing that is left unobserved, which is highlighted in pink, can be recovered using the rest of the three through this equality sign. So this is basically how we can recover the ATT in this situation. So essentially, without the minimum wage change, we expect the employment trend, okay? So these are all about the Ys. Okay, so we expect that the trend in the employment level is the same across both groups. So coming back to the maths, how does it actually work? So this is our common trend assumption. which basically is that we have the same before-after difference, absence of the treatment. Then if we bring the baseline outcome, the baseline observed outcome for the treatment group to the right-hand side of the equation, then we can essentially identify the counterfactual, the unobserved counterfactual for the treatment group at the end line. Now remember, this pink term is part of the ATT. It's the part of the ATT that we don't observe. The ATT is what we actually observe at the end line minus the counterfactual at the end line. But then given these two equations, essentially there is a way to re-identify the ATT. We simply subtract what we observe for the treatment group at the end line by all these terms on the right-hand side of the equation, okay? And that's why it's called the DID. It's the difference, so it's the difference, the middle difference, okay? So this middle difference term, and it's the difference in the differences. Then, given we know that the ATT can be identified using 4 means, then we can estimate them essentially using 4 group means. So we estimate them using the sample observed change over time between the treatment and the control group. So this is how we can recover ATT using simple means comparison. But how does that relate to regression or the causal model that we've been looking at? So essentially, in this situation, if we excluded other control variables, basically in the situation where we do have common trend, there's no need to control for other control variables. So if we postulate a linear causal model that takes this form, so what we have here is that the t, which is the time dummy, okay, so the t is equal to 1 if we're at the end line and 0 if it's at the baseline. Again, d corresponds to 1 in treatment group, 0 in control group. Now, for every individual yi, okay, so the I, actually we can have the same individual, but they're either in the baseline or in the end line. So we have a repeated cross-section here. Then, given that we have 2 dummies, okay, we call from topic 2. So dummy variable basically split our sample into subgroups. And given that we have 2 dummies characterizing different characteristics that basically separate our sample into 4 subgroups. Okay, so basically matching, T1, T0 with D1, D0, and similarly T0 with D1 and T0 with D0. Then, given the linear causal model, essentially we can write out 4 equations for each of the subgroups. So let's look at those in the control group. So if we look at those in the control group, basically this D is 0 and this D here is 0. So the phi1 bi term doesn't matter for the control group, and also the phi3 times the interaction term doesn't matter for our control group. And what we have is that, so given they're in the control group and at the baseline, the y is then just equal to the phi naught. The t is equal to 0, so it doesn't matter. And also the error term for this individual, given that at the baseline and also in the control group. Okay? And similarly, we have that when the t is 1, so we still have the phi naught, okay? But now t becomes 1, so we have the phi 2. And again, we'll also have the error term, but that corresponds to the end line. although still in the control group. Then a simple before-after analysis for those in the control group, that will have the phi naught term canceled out. And we'll have so it's yi given di is 0 at the end line minus yi given di is 0 at the baseline is equal to the phi 2 plus the differences in the error terms. Okay, so it's the end line outcome in a control group minus that at the baseline control group. Then averaging over everyone in the control group, you just simply take the expectation. So what we get is, okay, let me just use a different color to make it a bit more obvious. So that's the difference, and this is what we get. And you just simply take the expectation on both sides. The expectation of phi 2, which is just a constant, is itself, so we only need to take the expectation of this error term of the causal model. So this is what we get for those in the control group. Okay, everything here is causal. We're looking at a causal model, not the regression model. Now, if we now look at those in the treatment group, so the di are actually 1. This is 1, and this is also 1. For their baseline outcome, okay, so we're looking at those in the treatment group, but at the baseline, so the Ti is 0, that goes away. Now this Ti is also 0, that means the interaction term also goes away. So what we have for the treatment group at the baseline is then the phi naught plus the phi 1 times 1, which is just phi 1 itself. The rest of the terms are just 0, and what we're left is again the error term, given that 1 is at the baseline and 1 is in the treatment group. Okay? And similarly, if we now consider the end line, basically all the dummies will just equal to 1. So essentially, we'll have sum of all the coefficients for the treatment group at the end line. So that gives us the sum of all the phi's. Okay? And then plus the error term that collects everything. Everything else that affects y, okay? Then again, doing a before-after analysis for those in the treatment group, we'll see that the phi naught canceled out, the common phi 1s canceled out. So what is left is that we'll have the phi 2 plus the phi 3, and then plus the differences in the epsilons. Okay, so it's the end line minus the baseline for the treated group. So this is the before-after, so it's the after minus before, conditioning on you're in the treatment group. Okay, this is similarly the after and before, conditioning on you're in the control group. And if we again simply take the expectation, the phi's constant doesn't matter. It's just that we need to take the expectation of the error terms. Now, let's call the change in the error terms. These are essentially the trend, okay? One is the trend over time for the control group. right? We are subtracting the after from the before. And similarly, we have that the trend over time for the treated group, we're subtracting the after from the before for those in the treated. These are what we have so far are simply the before-after analysis for each groups, the treatment group and the control group. Then, how can we find DID? Remember, DID is the difference between the two before-after analysis. Essentially, what we have on the slide is what I'm doing here, okay, on my iPad. So, to find the DID, that is basically the difference between these two. We subtract the before-after for the treatment group from the before-after for the control group. So the overtime difference. So the before-after analysis, given you're in the treatment group, minus the before-after analysis, you're in the control group. Then if we look at these two, okay, so we're looking at the difference between these two equations. The common phi2 term canceled out, okay? This term canceled out. What is left is just the phi3 plus the trends in the epsilon. Then if the trends in the epsilons were the same, then we'll be able to recover the treatment effect. So that's why the common trend assumption is so important, okay? Regardless of we're simply comparing simple group means as by comparing four group means, or whether we're looking at regression analysis, the same common trend assumption will help us identify the ATT, okay? So this is equal to phi3 plus the trend, given that you're in the treatment group, minus the trend, given that you are in the control group. And this is equal to 0 under the common trend assumption. So we're done, okay? Under this assumption, essentially the phi3 is equal to DID, which basically makes it the same as ATT. So given that we have common trend, then the causal model satisfies OR. So the OLS, which consistently estimates the regression model, the population regression, that is mathematically equivalent to the causal model under OR, will also consistently estimate our ATT. Okay, I know there's a lot of maths here. Give yourself some time to go through it again after class. Try to redo sort of the manipulations. There's nothing hard here, it's just a lot of terms, but as long as you know what the terms are, you're fine. So the very final slide. It's all about the common trend assumption. So DID will only work if we do have common trend, which means if we have non-parallel trends, we'll never be able to consistently estimate the true treatment effect. Now, this assumption is not directly testable because it involves the untreated state outcome for those in the treatment group, absence of the treatment, which is the counterfactual outcome. But we could empirically test it if we have more data. This is the second best alternative. I mean, obviously the best option is invisible. Then we look at what other alternatives we can do. So in order to test for the common trend empirically, we require more than just 2 time points. So we need more pre-treatment time periods. And we hope that by having data on the more pre-treatment time periods observations, then we'll be able to check whether the trends are parallel in those pre-treatment period, that will tell us, at least give us a bit more confidence in that during the period where we're actually calculating the DID, they will have the same trend absence of the treatment. So if you look at what we have, okay, so imagine D at 0, so this time 0 is our actual baseline. And 1 corresponds to our actual end line. And if we have some pre-treatment, so we have more pre-treatment time points, so for example, we have it being -2, -1.5, you can think of it as if, a year before the baseline and half a year before the baseline, and similarly on this. So if we end up having parallel trends up to the baseline point, because after the baseline, we'll have the treatment, then we're fine. So that gives us some evidence that we do have parallel trends. But if instead we're on the left panel, or actually the right, okay, so obviously we can see that pre-baseline, New Jersey does not have the same trend for employment compared to Pennsylvania. And then obviously this violates the common trend assumption, and therefore DID will give us no hope in recovering the ATT. So if you were to use DID in practice, make sure you check the pre-treatment trend, whether they are the same. If they're different, then you will need to use some other estimation techniques that's different from DID. For example, regression discontinuity or the instrumental variable analysis that we've seen in topic 3. So pretty much this is it for the topic 5. And I think I managed to finish everything before 9:50. So just to give you a bit of heads up what might be there next week. Monday, no lecture. Friday, we're covering the mock exam paper. I'm not sure whether I'm going to use the all 2 hours, because there are 2 lectures scheduled on Friday. I'll definitely use the first one, 9 a.m. one, and see how far we can go with that mock exam paper. If I can manage to finish everything, which I hope I can, then I'm not going to use the second office hour that day, but I'll be in my office after the first lecture. I'll be holding my office hour. If you have any questions, you're more than welcome to drop by and ask. And also, next Tuesday, I'm going to release quiz 4, no pre-work. Okay, quiz 4 will be available at 10, so make sure you attend the quiz 4, which is related to topic 5. So thank you all for coming today. I hope that's not too much to take on, but in case I don't see you next week, thank you all for your hard work this academic year. It has been a great pleasure to see you consistently in the lecture throughout. So thank you very much, even though it's a 9 a.m. one. And all the best. Good luck with the exam.